I'm Sikiru Mohammed from School of Mechanical Engineering. I started my PhD journey exactly 2.5 years ago. This morning, I shall be making a presentation on my PhD research entitled Investigating Pitting Corrosion in Low-Carbon Steel. The terms contained in this topic will be made clear as I go on. The presentation shall cover introduction, where I'll give a brief on my background, corrosion overview, and define what pitting corrosion is about. I'll thereafter talk about my experimental work, beginning with a novel technique for generating corrosion pits, effect of corrosion products on pitting, and design of an improved artificial pit, before I talk about the impact of this research and finally concluding on this presentation. On my background, I obtained my Bachelor of Engineering from Nigerian Defense Academy and my master's degree from the same university. I've attended several career development institutions, both in Nigeria and outside Nigeria. Upon graduation, I was posted to the Nigerian Army Corps of Electrical and Mechanical Engineers. I've served in several United Nations operations, the latest being the United Nations Peacekeeping Force in Darfur as a Peacekeeping Force commander. Now we begin to wonder, what is the connection? What is the link? Military, PhD, engineering, I'll tell you. In one of my deployments in the military, I served in the Kiev engineering plant in Ukraine. And in this plant, we dealt with structural material. And I realized that low-carbon steel is of good choice to engineering design due to its low cost, availability, and ease of machining. However, despite the several corrosion mitigation efforts in place, corrosion still took place on these metals. It's just a function of time. And that aroused my interest into the corrosion field. Now, what is corrosion about? We all use metals one way or the other. Automobiles, buildings, even in our kitchen, our cooking utensils, we see steel everywhere. Do we imagine why this steel always corrode or rust? It is simply because metals exist naturally as ores, but are often refined to make useful product of them. Corrosion is a natural phenomenon in which these metals return back to their state of ores. And corrosion will always tend to occur because the ore state is more stable than the refined product. Now, corrosion is the cause of dilapidation we see, like the corroded bridge we are seeing on the screen. In our homes, it is the cause of brown water we see running on taps at times. Even the medical field is not spared of corrosion. So medical procedures such as hips replacement are also confronted with the problem of corrosion. What about the oil and gas industry? What you just see on the screen is an hazard caused as a result of corrosion of pipeline. You can imagine the effect of this on health and safety, depletion of ozone layer, the global warming we're always shouting about. This is part of corrosion effect. Even the aviation industry is not spared of corrosion. The image just displayed is an Aloha flight aircraft that was destroyed on flight as a result of corrosion to the fuselage. I can continue to go on and on across all disciplines. Corrosion is just everywhere. But for want of time, let's look at the cost. Globally, corrosion costs 3.4% of the entire world GDP. We are talking about $2.5 trillion annually. What about in the United Kingdom? 46 billion pounds annually going to corrosion. This amount is enough to cater for over 700,000 social homes annually in the United Kingdom. Of all corrosion types, pitting corrosion is the most devastating form of corrosion attack. Now, what is pitting corrosion? Pitting corrosion is a sort of extreme dissolution of metals. We see this at times in some metals, a kind of patchy spots, but we never take note of them. These are what? Pitting corrosion. Pitting can continue undetected until eventual rupture occurs on metals. My PhD research is looking at how to understand pitting and provide mitigation to prevent its menace. How am I doing it? 3 important gaps have been identified in the course of this research. The first being ability to generate reproducible pits in the lab for investigation. For you to understand pitting, you need to have it in the lab, study it well, and also provide ways of mitigation. In the past, effort at doing this has been through the use of what? Nano indentation. What is nano indentation? It's a mechanical device you use to impinge a kind of pitting pattern on metals. However, the nano indentation induced mechanical stress on the metal. And this does not reflect the true pitting we see on the field. Another method is use of acid to etch metals and get pitting. However, this is not repeatable. And besides, it takes a longer time to do. My work is able to provide a means of generating this pit reliably. Now to the second gap. How does corrosion product influence pitting? Okay, what is corrosion product? Any metal exposed to the atmosphere have corrosion products formed on them. We don't see these corrosion products with our eyes, but this is one of the reasons why we use Brazil at times to shine these metals to restore their shine. It is corrosion products you are cleaning. My work is able to show that different corrosion products that forms on metals influence the extent of pitting. I will show this later. Now to the third gap of my research. What events occur inside an actively corroding pit? Yes, a corrosion pit has occurred. What we see on the surface, the corrosion product, is likely to be different from what is happening right inside the pit. My work is able to design an artificial pit, which I have here today, and I'll pass it when I'm discussing this. Let's look at the first gap I'm looking at, which is generating reproducible pits on steel surface. The method used is by use of voltages to generate corrosion pits. What we are seeing on the screen is roughness induced by 50 millivolt potential static on the metals. Now, if I decide to increase this potential to 100 millivolts, you can see the roughness increase, right? Now, let's go to 150 millivolts. Here, we can see distinct pitting on the metal. What we are seeing for 50 and 100 millivolts is more of uniform corrosion, on the surface. But the moment you go to 150 millivolts, you have both uniform corrosion and pitting recorded on the surface. This may not be too clear. Let's look at the 3D images, the 3D. For the 50 millivolts, the roughness was about 26 micron pitting. Increasing to 100 millivolts, 55 microns pitting. And going to 150 millivolts, we have 120 microns pitting. Now, what are the advantages of this method? Why is it different? It has the ability to generate repeatable pits in practical time frame, ability to induce pit with no deformation, ability to control pit size through the applied potential threshold, and ability to induce high corrosion rate in practical time frame. Now let's look at my second gap, which is talking about corrosion products that form on surface. We don't see this with our eyes, but with equipment, such as scanning electron microscope, you can see this. What we are seeing on the screen is in calcium environment, and this is what we call amorphous layer. What is amorphous layer? It means it has no defined shape. You can't really say this is a shape. Now, in calcium environment, we have this. What of in a salty environment, in the same calcium environment, we have what we term as aragonite. Then in an environment with higher salt concentration, you have aragonite and verterite, the mixture. If you decide to raise the temperature, like places that have higher temperature, you have mixed carbonate. My research is able to show that how pitting trend under these conditions are all different. Let's look at this. Under aragonite condition, for instance, experiment conducted in the lab yielded 160 microns depth. However, in mixed carbonate condition, we generated 54 microns under the same duration of time. So with this, we can tell engineers in the field, set your parameters to environment favoring this to minimize the effect of pitting. That is what this is aimed at. Now, going to the third gap, which is talking about the artificial pit. The artificial pit designed is shown on the screen. And the novelty in this design is the improvisation of the nylon bolt. In that nylon bolt is a piece of material, the anode pin, which is of the same material with the cathode disc, right? We can unscrew this bolt out and in to vary the pitting profile. And with this, we can play out different pitting profile, for laboratory investigation. An electrical connection is made to collect our electrochemical measurements. I have the artificial pit design here, which I would like to pass to the audience. I'll drop this vessel to minimize risk of accident. The bolt is just right in. As you turn this, you tend to vary the pitting profile. I leave that with you. Yeah, why I go on? What's the impact of this research? Let's look at that. This research has been presented in several conferences. In the year 2017 National Association of Corrosion Engineers Conference in Louisiana, USA, it has been presented in the European Corrosion Conference 2017 in Prague, Czech Republic. It has been presented in the 57th Corrosion Science Symposium in Swansea, and also the 58th Corrosion Science Symposium in Birmingham in the year 2017. The work on the first gap, which is the peat propagation, has been published and has received significant attention and recommendation based on ResearchGate statistics. Other work on the two gaps, the manuscripts are ready and to be published shortly, very soon. Research in progress. This current work is being utilized by some PhD students in this university now, and also some year 3 engineering projects. We've also had calls from Saudi Arabia and some universities outside the United Kingdom on guide on how to apply this technique. On the long-term impact, this work is capable of being used to predict corrosion failure, right? Thereby minimizing the global costs associated with corrosion menace. The methodology is also applicable for use in all range of metals. Then this work can also be applied in selecting inhibitors that is capable of being used to retard corrosion in metals. And in doing so, what are we doing? We are reducing the probability of degradation, minimizing occurrence of oil spill, reducing equipment downtime, and disruption of supply of essential services. Now, the research work I've presented here today is all geared towards protecting people, assets, and environment from the effect of corrosion, in line with the National Association of Corrosion Engineers mandate. And finally, I'm leaving you with a word before I leave, that corrosion is here. It is everywhere around us, and you cannot run away from corrosion as long as you do with metals. Thank you for listening. I'm happy to take questions.
Thank you very much. And we open it to the panel. We've got a couple of minutes if there's a question from the panel. Again, they're writing furiously.
Have you, what's the sort of cost implications?
The cost implication of this,
yeah.
Everything can be done with just $100. It's not expensive. Yeah. It's just machining, getting the shape you want, putting it into resin, mapping out the area you want to work with, and getting simple connections. It depends on the environment you want to work on again. For instance, if you are working in a sulfur environment where you have high sulfur concentration, then you have to start thinking of that sulfur gas, to play out the experiment. If you are working in carbon dioxide environment, you have to start thinking of that supply. And if it's in normal atmosphere like this, then you just put it in your vessel and keep going. Yeah.
Excellent. Thank you. Is there a further question, or are we okay? I think they've gone quite quiet. I think we're okay there. So thank you very much. Thank you. Sikiru. Thank you.